every possible projection from the outer surface of the airplane. Everything that would induce turbulence with its attendant drag must be reduced to a minimum. The use of a rivet whose head is flush with the surface being riveted eliminates the drag of the ordinary rivet head and thus aids in accomplishing our higher speeds. The choice of method to be used in flush riveting is based on the thickness of the sheet next to the manufactured head. Let's assume we're driving a rivet 1/8 inch in diameter with a 100-degree countersunk head. Probably the best production method involves sheets of 40 thousandths thickness or greater. We start with the assembly of the sheets, drilling the correct size hole for the given rivet. We're using a 1/8 inch rivet, so we drill a number 30 hole, then countersink, using a special countersinking tool with a 2-flute cutter and with a 100-degree cutting angle and number 30 pilot. Unless specific approval has been obtained from the stress engineer, the countersinking should not go through the first sheet. If sheets are properly clamped during countersinking, it is not necessary to disassemble them for burring, which is a costly operation. Next, we insert the rivet, the length of which has been determined by adding 1 1/2 times the diameter of the rivet to the grip. The grip, as shown here in white, is equal to the total thickness of the material being riveted. A vibrating type air gun with a flush rivet set and a regular bucking bar may be used. Ordinary riveting technique will do for driving of this type rivet. The finished rivet should have a formed head, 1 1/3 times the diameter of the rivet and about 1/2 the diameter high. The flushness of the rivet, as determined by aerodynamics, must run in the neighborhood of plus or minus 2 thousandths. We have just demonstrated the countersink method of riveting. This is a method used when both sheets are over 40 thousandths in thickness. Structural requirements make it necessary to dimple the sheet next to the manufactured head if this sheet is under 40 thousandths in thickness. This double dimple method is used for flush riveting thin sheets. Here again, we start with the number 30 hole and follow this with insertion of the rivet. The length of the rivet is again the thickness of the material plus 1 1/2 times the rivet's diameter. The driver uses a standard flush rivet set. The bucker uses a special dimpling set that has been adjusted by the tool department to give the correct angle and depth of the dimple. Using the rivet as a punch, we dimple the two sheets together into the dimpling set. The special dimpling set is removed. The driver retains the standard flush driving set. The work then proceeds with the bucker using an ordinary bucking bar. Driving this type of rivet requires greater skill than was required in the previous method. Any clinching or offset of the rivet will cause the dimpled edge to crack. The rivet must be driven straight. We have just shown the double dimple method of riveting. This is one of the methods used when both sheets total 40 thousandths or less in thickness. A third method, used for riveting of slightly heavier gauges than in the last method, involves a separate dimpling of the sheets. Again, we start by drilling our number 30 hole. The sheets are then disassembled and machine dimpled separately on the squeezer. Note the angle of the dimpling tools. The dimpling punch for the top sheet has an angle of 100 degrees, the same as the rivet head. The dimpling die has an angle of 110 degrees. The dimpling punch for the bottom sheet is also 110 degrees to correspond with the top sheet, and the dimpling die is 120 degrees. This difference is necessary in order to get a good nesting of parts. Upon completion of the dimpling operation, the parts are reassembled. Sheet metal riveting clamps are used to hold the parts together until riveting is completed. The rivet is inserted, and from here on the work proceeds using a regular flush riveting set and the ordinary bucking bar. Driving this type of rivet requires the same skill on the part of the operator as in the former dimpled method. It is very important that the rivet be driven straight. We have just illustrated the pre-dimple method of riveting. The sheets were taken apart and machine dimpled separately on the squeezer. This is the method used when the sheets are too heavy for the double dimple process. For sheet gauges where the top sheet is too thin to countersink and the bottom sheet too thick to dimple, we must use a combination of pre-dimpling and countersinking. The top sheet, being under 40 thousandths, must be dimpled. The bottom sheet, being over 40 thousandths, will be countersunk. Again, we start by drilling a number 30 hole. Sheets are disassembled and the upper sheet is machine dimpled using special dimpling tools on a squeezer-type machine. The bottom sheet is countersunk using the special countersinking tool. The angles of the dimple and countersink are very important. The angle of the dimple next to the rivet must be 100 degrees because the rivet head is 100 degrees. The angle on the opposite side of the sheet is 110 degrees. The angle of the countersink is also 110 degrees. Parts are reassembled using sheet metal clamps. Rivet is inserted. This is followed by driving the rivet using a standard flush driving set and bucking bar. This riveting technique is fairly simple because there is no lip on the undersheet to cause cracking or failure from clincher rivets. We have just demonstrated the combined countersink and dimple method of flush riveting. This combination is used in cases where the sheet next to the rivet's manufactured head is too thin to be countersunk and the bottom sheet is too thick to be dimpled. Now let's review the four methods of flush riveting just demonstrated. Countersinking, used when the top sheet is 40 thousandths thickness or greater. The flushness of the rivet is obtained by setting it into a hole countersunk by a special tool. Double dimpling, used when the total thickness of the sheets being riveted is 40 thousandths or less. In this method, the flushness of the rivet is obtained by using the rivet itself as the punch to form the dimple. Pre-dimpling, used when the top sheet is 40 thousandths or less, and the total thickness of both sheets is over 40 thousandths and under 90 thousandths. The flushness of the rivet is obtained by setting it into a dimple formed mechanically on a squeezer. Combination, countersinking, and dimpling, used when the top sheet is too thin to countersink and the bottom sheet is too thick to dimple. The top sheet is dimpled and the bottom sheet is countersunk. The result obtained by each of these different methods is the same. The head of the rivet is flush with the surface so that the turbulence or drag is held to a minimum. With the ever-increasing demand for greater speeds in aircraft, it has been necessary to remove every possible projection from the outer surface of the airplane. Everything that would induce turbulence with its attendant drag must be reduced to a minimum. The use of a rivet, whose head is flush with the surface being riveted, eliminates the drag of the ordinary rivet head and thus aids in a